Greetings, AP Chemistry students. Today we're going to talk some more about electrochemistry and electrolysis and all that good stuff. I want to start us off with this free response problem where a student sets up a galvanic cell with a silver electrode immersed in a 1 molar solution of a silver solution and an electrode of chromium immersed in a 1 molar chromium 3 plus solution, as shown in the diagram above. So the student measures the voltage of the cell and discovers that it is zero, identify the missing component of the cell, and explain its importance for obtaining a non zero voltage. So what's missing is the salt bridge, which the salt bridge would kind of go here. And its importance is to provide a balance charge, right? Because as this cell runs, well, we'll look a little bit more at this. It says the student adds the missing component to the cell and measures the cell potential to be positive 1.54 volts. As the cell operates, silver ions are reduced. Okay. So if silver ions are reduced, that means that this reaction runs as written. That's a reduction half reaction. And this reaction has to run in reverse. And so the cell potential for chromium, because you have to have something reduced and something oxidized, the cell potential for something being oxidized here, for the chromium being oxidized, if the total cell voltage is 1.54, this would be 0.74 volts. So the cell potential for the reduction half reaction they give you down here in part one would be negative 0.74 volts. And then it wants us to write a balanced net ionic equation for the reaction that occurs. Well, this top reaction, the silver reaction, we're going to have to triple that. So our overall reaction would be that 3 Ag pluses plus Cr makes 3 Ags plus Cr with a positive 3 charge. So that would be the net ionic equation. The electrons would cancel out, right? And then it says calculate the value of delta G. Well, delta G equals negative NFE, and N is moles of electrons transferred, which in this reaction is 3. Because we have 3 silvers being reduced, so that's 3 electrons there. We have chromium being oxidized, that's 3 electrons, same electrons. Times Faraday's constant, which is 96,485, times the cell potential, which it says is 1.54 volts. So we take our trusty calculator, negative 3 times 96,485 times 1.54, and our value for Gibbs free energy is negative 446 kilojoules. But it wants it in joules per mole. So it's going to be negative 446,000 joules per mole. Now, one thing I do want to point out, I mentioned this to the folks who were in class for this lesson, but the reason that we don't multiply the value of E by an integer value when we triple a reaction, the reason this doesn't get tripled here is that tripling the reaction gets accounted for in our delta G equals negative NFE because the electrons are tripled there. That's where things get tripled. It does not change the driving force of this reaction. It's electrical potential. That remains unchanged. Now, I want to look a little bit more at this reaction. So since silver is being reduced, that means that silver ions are being plated out onto the silver electrode, while chromium metal is going into solution. So if you started with each of these electrodes weighing 25 grams and you let the cell run, after a while, the silver electrode will have gained mass, while the chromium electrode will have lost mass because those metal atoms are going into solution. Now, since we're putting chromium ions into solution over here, we're dumping positive charges into the left container and we're removing positive charges from the right container. That creates some more problems. That's why we need the salt bridge. So, if our salt bridge contains, for instance, let's go with KCl. Well, what's going to happen is that since we're dumping positive ions in there, the Cl minuses are going to go this way, while the potassium ions are going to go this way to replace the silver ions that have been removed from the solution. So you need to balance the electrical charge. Also, since electrons are being gained by the silver, the electrons would flow through the wire from the left side to the right side. So let's say if the cell ran for 10 minutes and the current was 5 amps, how much silver is produced? Well, we know that I equals Q over T. So our current is 5 amps equals Q over our time in seconds. So that would be 600 seconds. So Q equals 5 times 600, which is 3,000 coulombs. And then we know that there are 96,485 coulombs in 1 mole of electrons. Then for every 1 mole of electrons, we get 1 mole of silver because it's a 1-to-1 ratio down there. And then we would multiply this by the molar mass of silver. So that would be one. We would multiply that by 107.87 grams per mole. So that would give us a total of 3.4 grams. Now, if we had wanted to figure out how much chromium was lost, well, that would change two things in our calculation. Instead of a 1-to-1 ratio, it would be a 3 moles of electrons to 1 mole of chromium. And then obviously we would plug in the molar mass of chromium instead. So that's kind of an introduction to some of these calculations. I want us to look at a couple more things, though, before we wrap this lesson up today. So first, we've got this kind of shows how iron actually corrodes. If you have a water droplet present, what happens is iron gets oxidized into iron 2, which is rust. That would be the anode. And the cathode reaction is that oxygen plus water is reduced into hydroxides. So the oxygen and water are both required to be present, which is why iron things rust when it rains. This next thing shows how you can actually protect things like if you have a buried cast iron pipe, you can take something that has a higher electrical potential, a higher oxidation potential, is more easily oxidized, like magnesium, and attach it to it with a wire where the magnesium will become oxidized and rust away while protecting the iron. A similar thing is done with boats and ships where they will actually take pieces of zinc or sometimes magnesium, it's just zinc is a lot cheaper, and bolt it to the side of the hull because those things are more easily oxidized. In a water heater, typically a, a hot water heater at your house uh, has a rod that's made has an anode rod made out of aluminum usually because aluminum ions are relatively inert and aluminum is more easily oxidized. And so that's in there to protect your steel tank and your hot water heater from rusting away. The other thing I want to look at real quick is electrolysis or electrolytic cells. These are ones that require energy. So, electrolysis is when you're forcing a current through a cell to produce a chemical reaction for which delta E is negative, or for which E is negative and delta G is negative. And in an electrolytic cell, the most positive oxidation and reduction half reactions will occur. So if you had a mixture of things present, typically the thing that is most easily oxidized and most easily reduced, those will be the reactions that happen. We'll actually do a lab experiment with this where you'll actually do some electrolysis. Um, well, I'll explain some of this in more detail with actual examples tomorrow. But applications of electrolysis, it's used to isolate metals from molten salts. Uh, so if you want to produce sodium metal and chlorine gas, you can melt sodium chloride and apply electricity to it. That's in fact how most of these alkali metals were initially discovered, is through hooking up a battery to some melted salts. If the salts are dissolved in water, water is very easily oxidized or reduced compared to the compounds and salts. So sometimes you will end up producing, instead of producing sodium and chlorine, you would produce hydrogen and oxygen by electrolyzing the water. But there is this thing called overvoltage where sometimes you get an unexpected reactant produced because one of the reactions has a very high activation energy. Electrolysis is also used for electroplating metals. For instance, a lot of audio cables are gold plated with just a very thin 1 to 2 atoms thick layer of gold over the surface of them. Or jewelry is plated with gold. There's a very, very, very thin, microscopically thin layer of gold over something much less expensive. Electrolysis is also used to recharge batteries. Now, it can be very dangerous to try to recharge a non rechargeable battery because instead of reversing the reaction, you may start breaking apart the water that's in the cell and filling the battery up with hydrogen gas, which creates a very dangerous situation. Um, so, this is kind of showing if you had a standard galvanic cell, and then if you had a power source greater than 1.1 volts in the reverse direction, you can reverse bias this and make the reaction run backwards. Right. So, hope that gives you a little bit of an understanding of how this works. And hope you'll have a fantastic day.